Welcome to the WISE Confidence Interval Creation Applet. This video will give you a brief review of confidence intervals. We'll demonstrate an applet that shows how confidence intervals can be constructed, and we also will demonstrate some of the interpretations and limitations of confidence intervals. I'm Dale Berger. I'm a professor of psychology at Claremont Graduate University. This applet is one of many resources that we have available on our website. You see the URL here, wise.cgu.edu, and you're welcome to explore all of these resources. Just a quick reminder of confidence intervals. The goal is to identify a lower and an upper limit bounds for a population mean based on a sample. For example, we might have 30 cases that we've drawn randomly from a population with an unknown mean. Our sample mean is 510 with a standard deviation of 90. And the question is, what are the limits of a 95% confidence interval for the population mean? The first step might be to summarize this information. N represents a sample size. In this example, N is 30. We've drawn a mean. The sample mean in this case is 510. The standard deviation is 90. And the t-value will be used to identify the cutoff points. For example, if we want a 95% confidence interval, we'll choose a t-value that cuts off 95% in the middle of the distribution and only 2.5% then on each end of the distribution. The limits of the interval can be calculated as follows. The lower limit, we start with the mean. The first step is to find the standard error of the mean. Now, the standard error of the mean is an estimate of the standard deviation of possible means that we could have gotten for samples of size n. In our case, n is 30. The standard error of the mean is the standard deviation of the sample divided by the square root of n. The central limit theorem describes this, so we have a tutorial on that you could check out if you need to brush up on that. And then the t-value, this symbol represents the alpha level. Alpha 0.05 is a standard level. Alpha divided by 2 it refers to this being a two-tail test that cuts off 2.5% then on each tail. The degrees of freedom are associated with the estimate of the standard deviation. With a sample of 30, the degrees of freedom on the sample standard deviation would be 29. So we take the standard error of the mean and multiply it by the t to get the likely error. That is, how much above or below the mean we might be likely to observe. And so we begin then with our sample mean and we subtract the likely error, and in our case the likely error is 33.6. So this gives us a lower bound then of 476.4. The upper bound is found in a similar way. We add the likely error to our sample mean. In this case we add 33.6 to the 510 and we get 543.6. Now we can use that information to make a confidence interval. The confidence interval would look like this. Confidence interval is commonly misinterpreted. Here are some wrong interpretations. The population mean is between 476.4 and 543 95% of the time, or the probability that the population mean is in this interval is 95%. So what's wrong with those interpretations is that the population mean is a constant. We don't know what it is, but it's a constant. It's a value that's fixed. It's written in the dust on the backside of the moon. Nobody knows what it is, but it's a fixed number. So it doesn't fall in this interval sometimes and not in this interval at other times. It's the interval that in fact has the probability associated with it. That's the stochastic process that bounces around. If we were to draw a different sample, we would get a different confidence interval. If we have done everything correctly, 95% of the confidence intervals constructed in that way would contain the true population mean. So that's a sense of the confidence interval and the probability associated with it. We might say the probability that this interval includes a population mean is 95%. Let's turn to the applet itself. and we have it loaded already. So this is what the applet looks like. The first thing to notice is the blue distribution is a representation of the population. This example, the population mean is 500 with a standard deviation of about 100. In fact, the parameters are given up here, the mean of 500, standard deviation of 100. We will be able to look at different types of distributions, not necessarily normal. We'll look at skewed distributions. We can press a button to get a skewed distribution, or skewed binomial, or essentially a dichotomous distribution, two bins widely separated. Or we can make our own distributions, and we can do that just by sliding the cursor, holding down the left mouse and moving a cursor whatever shape we want. Let's make it high here and down here and a little bit at the end. And so what we find then is the population mean, and we can then explore confidence intervals for any distribution that we wish. We can also choose whether we want a 95% confidence interval or a 99 or a 90. We can also change the size of the sample that we will draw, ranging from 5 up to 100. We can set it, say, at 30. If we get close, we can use the left arrow key to move it one at a time to get it exactly where we want. Let's go back to the case where we have a normal distribution and a sample size 30 with a 95% confidence interval. We can simulate drawing a sample of size 30 from this population by pressing the sample button. When I press the button, we see the representation of our sample. We also see a representation of the confidence interval. The confidence interval in this case includes the true population mean. The sample statistics are given below. In this case, the sample mean is 519, standard deviation of 91. If we want to see how the calculations work, we can press the calculation button, and we see the lower limit is begins with the observed mean, and we subtract t times the standard deviation divided by the square root of n to get the lower limit, and we take this likely error and add it to the sample mean to get the upper limit, 482 to 551. So we could say, and we can close the calculations by just pressing the button again. So we could say there's a 95% chance that this confidence interval that we created in fact encloses the true population mean. Now in practice we won't know, but if we've done everything right, we can have 95% confidence that we have captured the true population mean. It's important to recognize that this sample that we drew is just one of many possible samples. We could imagine that someone else did the very same study, sampled 30 cases from the same population, and let's see what they found. We press the sample button, our confidence interval drops below, and here is their confidence interval. Now their limits are somewhat different from ours. They have a somewhat wider confidence interval, but they also have managed to enclose and capture the population mean. Now with the 95% confidence interval, we expect only about 19 out of 20 confidence intervals will in fact capture the population mean. Let's do some more samples and see what we find. This now simulates different people. Any one person doesn't in fact draw 20 samples, but you might see what would happen if 20 different people did. Here's another person, captured it, fourth person, a fifth person. Now here is somebody who has a very nice sample, looks reasonably normal, but their confidence interval in fact does not include the population mean. They are blissfully unaware of this, however. Let's see, another person missed it. Let's go on and do about 20 of these. We would expect on average about 1 out of 20 would miss it. We could try another set of 20 to see that each person gets a different confidence interval. This time out of the 20, nobody missed it. And I'll do one more set of 20. We would expect about 1 in 20. Sometimes you get none, sometimes you get 1, and sometimes you get more than 1. How would the confidence interval be different if we had a larger sample? Let's consider a case where we have a very large sample. Would we expect the confidence interval to be larger or smaller? Well, with larger samples, we have more precision. And we see the confidence interval, in fact, is very small. We'll do 20 of these to get a sense of typical confidence intervals when n is this large. And we see that, in fact, they are all much smaller than the confidence intervals we saw earlier. However, if we've done things correctly, still we expect about 1 in 20 would fail to capture the true population mean. What if we have a much smaller sample? Let's go down to a ridiculously small sample size of 5. And what would you expect the confidence intervals to look like here? Well, we have less precision and the confidence intervals are much wider. Now, what percent of these confidence intervals would you expect to capture the true population mean? Well, if we're sampling from a normal distribution and we've taken random samples, we again should just have 95% confidence that about 19 out of 20 should capture the population mean. Here we had 18 out of 20. But what if the population is not normal? We have built in several skewed distributions or distributions that depart from normal. Here's a very skewed distribution. Let's see what happens if we draw samples from a distribution like this. Here's a case where someone had a sample like this. It would look pretty good. You wouldn't maybe realize you were sampling from such a skewed distribution. Here's another person who has a very nice tidy sample, but the confidence interval for this sample does not capture the population mean. I'll draw 20 of these to see the variety here. We notice several things. One is that these confidence intervals vary a great deal in size. That's because of the skew in the distribution. If we happen to have scores in the tail of the distribution, the confidence interval is wider. If we fail to get scores in the tail, the confidence intervals are narrower, but in fact may miss the population mean. We also notice that a higher proportion of the confidence intervals in fact did not capture the population mean. I did this 1,000 times and found that out of the 1,000 times, 148 did not capture the population mean. That's about 15%. So if we were sampling from a population that was skewed like this one, we might think we're calculating 95% confidence intervals, but in fact they would only be 85% confidence intervals. So we can see that's problematic here. We have a few other built-in distributions that are not normal. Here's a skewed bimodal. There are two bumps. Perhaps this represents two subsets of cases, maybe two different categories that are put together that we may be unaware of. But if we draw samples from this population, here a strange thing happens. The confidence limit, the lower limit of this confidence interval, is actually lower than the smallest score in our population. Why is that? Well, if you actually were sampling from a normal distribution that had a standard deviation as large as we find in our sample, a normal distribution like that would have scores that are farther off on the left side. So again, we see that we can run into problems with doing a confidence interval with a skewed distribution and a small sample. I'll do about 20 of these also to get a sense of the variety of outcomes. Again, note that any one outcome that we observe would be representing what one individual might find when they ran a study like this. And so we find that there are several that go off the limit of what's possible. I'll do a bunch more here just to get a sense for it. And we also see that there are quite a few that fail to capture the population mean. Let's try another one. This is a two-bin example. It's similar to a binomial distribution, although we have a distribution of scores in each of these bins. Here, if we draw a sample, and if they all happen to come from the smaller bin, we would get a very tight confidence interval, but it would miss the mean of the population. And I'll draw several of these. Oops, now there's one that's much larger, and that's because we do in fact have an observation from the other bin. So this is a pretty ridiculous application of applying confidence interval. The implication here would be if you have a population that does have outliers, those outliers can distort your population mean substantially, and the confidence interval that you would get just is not accurate to the actual population mean. What if we have a much larger sample? How helpful will that be? Let's increase the sample all the way up to 100 and use this crazy distribution and see how the confidence interval works. Well, this one captures a population mean, so does this one, and in fact, overall, we find that the confidence intervals are much smaller, and we do a fairly good job of capturing the population mean. We still have bias. It's not truly a 95% confidence interval, but this shows that with larger samples, in fact, the sampling distributions of the mean does approach normal, and the confidence intervals are not that far off. We can take one that doesn't look as bad and draw samples from it, and we see that in fact the confidence interval procedure is doing a pretty good job. Finally, this applet allows us to build any shape population we wish. We just hold down our left mouse and sweep over the distribution and make a nice funny one like this, and we can now draw samples from that and see how well the confidence interval procedure would work for a weird distribution like that. Again, with a very large sample, you can get away with more than you can if you have a small sample. So, what is our take-home message from all of this? One important lesson is that if a population distribution is not normal, a confidence interval may not be very accurate, and that's especially true with small samples. But even with large samples, we can see a degree of bias when we have a departure from a normality. So question is, what can you do? One alternative to consider is bootstrapping. Bootstrapping does not require the normality assumption. You still have problems with small samples and strange distributions, but the confidence intervals are more reflective of the actual distributions rather than assuming that you have a normal distribution when you don't. If you're interested in this, I suggest the bootstrapping applet tutorial that we have on our website. And finally, I'd like to introduce our WISE team. These are, we call the WISE guys and gal, as of May 2014. The person on the far right is Chris Pentany, who programmed this. He can program anything. We're very proud of him. Well, I hope you enjoyed this presentation. Thank you for your attention. And again, we encourage you to take a look at our website.